everyone. So welcome to another talk of this session. So we have Aritrabha Majumdar here, interested in probability and theoretical physics, statistical physics. So he is going to give a talk on random fractal percolation and related models. So over to him.
Thank you very much, Anuja, for the introduction. So before starting random fractal percolation, what I would like to say is like some basic setup of the percolation on the integer lattice. I hope most of you know that, but still it is good to have a recap. So when we define the percolation on Z2, what we do is we take the integer lattice. This is the origin, and like these are all the integer points which form the grid lines together like this. So the model basically goes on like this. These are all the lattice points in Z2, and the grid lines present between them, they work just like a channel to pass water or something like a bond, you can say. And each of these pathways or bonds, they are like open with probability p and they are closed with probability 1 minus p. So basically what we do, we connect an infinite water source or water channel here, and after that some of these paths are open. So I might use another color for that, that's helpful. So let's say this path is open, after that this path is also open, this is open, this is open. Just like this, things go on and on and on. And through these open paths, the water gradually escapes to infinity. So in some cases, these connected integer points together, they form a cluster, and this cluster can be either finite or infinite. So in order to study this in usual side percolation or bond percolation in ZD rather than in Z2 only, we define a thing that is known as chi of p, and this chi of p is known as the mean cluster size. So this mean cluster size or chi p, obviously there is a p in the subscript, so you can have some kind of assumption that this depends on the value of p itself. And this mean cluster size, sometimes it is finite, and after a certain value of p, this expected value of chi p rather, this basically becomes infinite. So after a certain or particular value of p, the mean cluster size present in normal percolation or Bernoulli percolation in ZT or in Z2, that basically was finite before a certain value of p, and after that it becomes infinite. So that particular stage, in order to define that particular stage rigorously, we define another function that is theta sub p, and this theta sub p is like defined as infimum of all those p's such that expected value of chi p is equal to infinite. And we can define another thing that is theta p hat, which is supremum of all those p's such that expected value of chi p is finite. So now the interesting thing for Bernoulli percolation is this theta p and theta hat p coincides. So if we try to draw the graph of this particular theta p and theta hat p, this kinds of look like this. So like it starts over here, it stays 0 for some time. After that it grows and then it stabilizes. And you can see that the graph is kind of continuous here, and this particular value, this is kind of like the critical probability. So basically these are the corresponding critical probabilities, and so this in particular represents the phase transition of my Bernoulli percolation in ZB. And these two values are here equal because the phase transition that you can observe is continuous. But it is not necessarily the case for every possible percolation we have. So, I mean, this is kind of like the general setup for percolation. We have some kinds of bonds or sides, they are either open or closed with some probability. And here we are assuming that every possible bond is independent of each other and they are open with probability P or closed with probability 1 minus P. But this can be correlated in some sense, not in, I mean, they are not necessarily dependent on each other, or I mean, each of them can follow different probability distribution, many things can happen. So all of these correspond to different percolation models. But today what we are going to discuss is a completely different kind of percolation. I mean, the term percolation is kind of derived from a very interesting phenomena which is known as the RSW phenomena or Russo-Seymour-Welch phenomena. And that is, rather than being a percolative property, it is kind of like a topological property of subsets. So here what we are going to discuss is we will try to see how a random fractal looks like, and then we will see some left to right crossing probabilities and things like that for those random fractals. So that's why we call it a random fractal percolation. So it is nothing like we will have bonds and sides there and there will be water or some other liquid percolating through them. It is not like that. There will be some self-similar images and they will form a left to right or top to bottom crossing together. So having said that, okay, so as I have already said something about Russo-Seymour-Welch, so let me define that as well. So if we take a rectangle of aspect ratio rho, so that means we have a rectangle like this, the width is n and the length is rho n. So if we have a rectangle like that, Russo-Seymour-Welch basically provides a bound for the left to right crossing via a continuous self-subverting path, and this basically sometimes gives a upper bound. Like if we take a 3n cross 2n rectangle, it is something like 1 over 120, things like that. So these are not really our concern in this talk, but basically Russo-Seymour-Welch deals with these left to right crossings. So similar things we will also do, left to right or top to bottom crossings, but let's at first define what a fractal percolation is. So fractal percolation, this term was first introduced by Mandelbrot, and at first I will define the model for R2 and then we will generalize it further. So in R2, what we consider is the unit square. So like this is our unit square, and then we fix a particular value of it. Let's say that value is something like some n greater than equal to 2. Okay, for now we can assume n to be 2 because it will help you to draw the diagram a bit better. So n is equal to 2 means we will divide this unit square into n square meaning similar pieces. So these are n square meaning similar pieces. So we have again 4 rectangles, and by similarity here we mean their unique up to homogeny, and after that we choose a particular value p which lies in open 0, 1. And now what happens, each of these subsection, they are either allies with probability p or they die out with probability 1 minus p. So for an instance, let's say these two square dies and these two survives. So now we will consider these two squares again and we will again subdivide them further like this, and we will apply the same notion here once again. So here we might have 3 cancellations and here there might not be even any cancellation. And in the rest of them, we again apply the same thing like this. And here, these two might cancel, here everything might get cancelled, and that's how the entire thing progresses. So obviously you can see that it is not completely self-similar because there is a certain randomness introduced by a Bernoulli random variable. So in this case, we call this particular phenomena to be stochastically self-similar. So stochastically self-similar means that when you apply a particular probability law to a bigger set and you get a couple of self-similar sets, then you basically kind of scale down that particular probability law to an appropriate proportion and apply that same law over that not siblings, I would say offsprings, over that offsprings. So that's why it is known as stochastically self-similar. So we will again encounter this term stochastically self-similar when I introduce a more generalized version of this, that is random substitutions. But for now, I think this particular description is enough. So this is what Mandelbrot did for R2 and thinking n is equal to 2. But we can obviously define this in a more general setup. And for that, what we can do is we can fix a particular d, a particular natural number d, which is greater than or equal to 2. Okay, you can obviously define random fractal percolation over a line, but that would be some sort of, what can I say, some sort of isomorphism or homeomorphism to the Cantor set. So, that is not really a very useful thing to have. And so we fix a particular dimension greater than or equal to 2, and we will see the random fractal generation on the d-dimensional cube. And also we will fix some n greater than or equal to 2. And then we define x to be a Bernoulli random variable with parameter p, and this p obviously lies between 0, 1. And then we kind of extend the idea of d is equal to 2 to an abstraction, and that is we define sigma sub k to be the collection of all congruent subcubes at generation k. So, as in this example, these 4 apparently big squares were the first generation candidates, and all of them are congruent in itself, and they are similar to their parents, or homogeneically similar to their parents. So, basically for a particular generation k, this sigma sub k defines a collection of all congruent subcubes at a particular generation k. And you can obviously understand that for a particular generation k, the side length of those cubes would be 1 upon e to the power k. Okay? So all of them have this particular side length. And then we take a sequence of random variables xi, and they take map from sigma sub k to set 0, 1. And all of these xi's are basically I to power x that we have defined here. So basically, even if you consider this in 3D, so if you take n is equal to 2 here, so you have 4 cubes like this, each of them survives or dies, and you can kind of like by induction generalize this argument for any dimension you want. And after that we define a set q sub k as all those I from this set sigma k such that x sub I is 1. So qk is basically a set of all my surviving cubes, the cubes which have survived the slaughter. And for the limiting set, we can define the limiting set as q infinite k greater than equal to 1, qk. Obviously, we can define this intersection because you know that q0 is a superset of q1, is a superset of q2 and so on. So it basically forms a decreasing monotone class. So by taking the intersection, we can define the limiting set. Okay. So this is like the general d-dimensional idea to generate by random fractals. And after that, what can we say is like for a particular generation K, what can be the cardinality of this set Q? So, for an intuitive idea, if we try to define this for, let's say I have this for 2 dimensions only. So, it is like if I choose to be n is equal to 2, I will just erase all these iterations for now. So basically now it has total 4 number of offsprings, and the total number of surviving offsprings after the first round of slaughter is basically governed by sum of these 4 Bernoulli random variables. We all know that sum of Bernoulli random variable is essentially a binomial random variable. So in this case, the first round of slaughter that basically behaves like binomial 4, p, and for any kth stage, the total number of available squares in our hand would be n to the power dk. Because we are working with a unit cube, each of the congruent subcube has length 1 by n power k, and d is a corresponding dimension. So, the cardinality of the set qk behaves like binomial n power dk, comma. So, this is a really interesting observation, and it would eventually help us to get a really interesting info about this random fractal model. Alright. So now everyone can have a couple of questions like, okay, so we have a decreasing class of sets over here. We are defining the intersection of them to the intersection of qk. But what is the guarantee that it would eventually converge to some limiting model? Or even if it converges, what would be the limiting distribution? Or is there any case possible when my limiting set would be empty? So, in order to study all those cases, we need to have a little bit of digression, and for that I would at first define a particular example of branching process, that is the Galton-Watson branching process. So in Galton-Watson branching process, what we have is, we have a sequence of random variables x sub I greater than equal to 1, and x sub n plus 1, this is defined as summation I running from 1 to xn xi of I comma n. So this xi sub I comma n, these are basically my random variables, and all of these random variables are integer valued, and I should write that I and n, both of them belong to the set of natural numbers. So these are all integer valued rather than positive integer valued random variables, and all of them are IID to some xi, and we define n to be the expectation of xi. Okay. And now what we can define is, the result which we are going to observe, that is my z sub n, this becomes 0 almost surely if my value of m is less than equal to 1. So if some of you people know a little bit of probability theory 3, then you know that these can be easily derived using Gödel-Cantor lemma, but there are easier proofs which would invoke the idea of probability generating functions. So I would at first like to introduce that idea. So let's say, in order to prove this particular statement, that, okay, let me write the statement a bit clearly, that Zn is 0 almost surely if n is less than equal to 1. So if this thing happens, so I mean, if you want to prove this thing, then we can write that. So let's say we define P0, P1, P2, this particular probabilities. So what P0 represents, it is the probability of having 0 offspring in the next generation. P1 is the probability of having only one offspring in the next generation. P2 is the probability of having only two offspring in the next generation, and so on. And then we define another sequence of values, that is D0, D1, D2, and so on. D0 represents that my entire Galton branching tree dies out in the 0th generation. So obviously you can understand this is never possible, because we started with an initial condition. Okay, I haven't defined the initial conditions. Okay. So the initial condition was x not equal to 1. So the Galton tree always starts with one particular parent, and after that subsequent numbers of offsprings can be generated. So the entire tree dies out in the very okay, so you have question. Sorry.
We haven't defined Z.
I haven't defined Zn. Okay. Sorry. So instead of writing Zn, I might as well write this prefix. Okay. That's the second condition. Sorry. So this will be just xn. Alright. So D0 is basically 0 because as we are starting with only one generator, the entire tree dies out in a very 0th step. That can actually never happen. Then we have D1, D2, and so on. And here you can see that D1 is basically P0. Why? Because starting from X0, if in the next generation the particular parent of the tree is not having any possible children, then the entire process dies out. So D1 is basically P0. And then if we try to define D2, how D2 would look like? D2 is basically either the tree kind of dies out in first generation, or the probability that it dies out in 0th generation, or it dies out in the very first generation, and they can define it on like this. So basically what I am trying to say here is this D0, D1, D2, all of this will form an increasing sequence. Because if a particular tree dies out within the nth generation, then it could have died in any of the previous generations. So an upper bound can be given by summing up all the probabilities. Because probability is sub-additive. We all know that the probability of union of events is bounded above by summation of probability of events. So as this upper bound can be given, and each of these represents a value of particular probability. So this sequence is bounded below by 0, and then we have this particular increasing phenomena, and the entire thing is bounded above by 1. So this sequence, increasing sequence, converges to some particular value, and we tell that value to be D infinity. Or rather than D infinity, I should write it to be D for the sake of simplicity. So it converges to some particular value D, and now what I would do is I would try to define a recurrence relation for Dm. equation for Dm that looks like P naught plus P1 Dm minus 1 plus P2 Dm minus 2 square and so on. Okay, so why does it look like this? Because if there are, let's say, j many offsprings in my very first generation, and if they have to die out within nth generation, then basically each of their lineage should get died within n minus 1 generation, and so and each of the generation basically dies out with independent probabilities. So like, what can I say? So, see, I have here 3 particular children in a particular generation, and if they have to die out within a particular m step, so whatever be their number of descendants, they eventually have to die out within m generation. So basically it is like union of some disjoint events. So either they die out in the very first generation or in the 0th generation, or they die out in the first generation, or there are 2 descendants and they die out within Dm minus 2 generation, and so on. So this basically looks like a probability generating function, if you know, and we can define the probability generating function to be h of z, and that is a power series of z, p naught z plus p1 of z square, and so on. So this basically tells us that Dm is essentially equal to h of Dm minus 1. And if we take limit m tends to infinity, we know that this frequency will converge to some d. So this will give rise to a fixed point solution. P is equal to h of t. So if we can have the particular value of p is equal to h of t, I mean the fixed point solution, this is basically like the probability that that generation gets completely vanished within countably many steps. So now we want this particular equation to have only one fixed point solution, and that fixed point solution is b is equal to 1. Because b is equal to 1 is a very clear solution for this, because if you put 1 in both of the sides, h of 1 is basically your h of 1 turns out to be 1, and this is sum of all the probability values that has to be there. So we want 1 comma 1 to be the only fixed point of the solution. And you can see, I mean, this is a good exercise to try out, that this can only occur when n, which is h prime of 1, h prime is the first derivative, their value is less than equal to 1. And why that happens? Because this particular function h of z, if you take the first derivative, h of z is greater than equal to 0 for all z, so the function is increasing. And if you take the second derivative, the second derivative is also greater than equal to 0. So that tells us that the function is convex as well. So if you have a convex function along with this particular condition, so okay, I might use this board. So if you have a convex function which has this particular condition, that looks kind of like this, and if this is the line x equal to y, it just intersects it at this point, and it never intersects it before this point actually. And so that tells us that 1 comma 1 is the only possible solution, and that basically tells us that z equal to 1 is the only fixed point, or d is equal to 1 is the only fixed point of this particular equation, and that tells me this sequence eventually converges to 1. So if expected number of offspring in this Galton-Watson process is less than equal to 1, the entire tree eventually dies out. Okay. And okay, so how does this even matter? So if I come back to this particular model, okay, so for simplicity I am taking n is equal to 2 and I am only considering R2. And if I consider this particular model, it is, you can see that it is essentially a Galton-Watson branching process. So at first you had only one square like this, then it gave 4 squares, and some of them survived, some of them died out, and the process basically continued like that. So fractal percolation, or the usual Mandelbrot fractal percolation in n is equal to 2 and d is equal to 2. You can say it is basically a Galton branching process with the underlying offspring distribution or zeta sub I comma j to be Bernoulli P. And as you are taking summation of Bernoulli random variables there, we got the cardinality of qk to be a binomial random variable. Yes.
Okay, you defined as the set of all I belongs to sigma k, right?
Yes.
But if it is like set of all I, then qk is not a superset of qk plus 1 because it would be like the union of I or something like that. So think of it.
qk is basically all of those surviving i's.
Yeah, but think of it like this, like in the like 2 plus 2 model.
Okay, the 2 plus 2 model.
Let's say 2 sets survive. Okay, like
okay, so I later assume these 2 times.
yeah.
Okay.
So the Q1 is basically that set, the first set, the 1 set and 2 set, right?
Okay, yeah. So like you can mark them to be like 1, 2, 3, 4. 2 and 3 died, 1 and 4
1 and
survived.
4, right? And then so it is a set of 1, 4.
Yes.
And then after that you will have a set of some subsets of 1 and 4.
Okay, so 1 and 4 are not like numbers. They are rather, I should say that they are the identifiers of these bigger rectangles.
Yeah, but then like when you're saying that this is a subset of the previous set, so you have to give the union. Otherwise you can't take a subset. If you take the union of both 1 and 4, then you can say that it's a subset, like superset of the next set, because it would be union of the subsets of 1 and 4.
No, see. So basically this qk. Okay, so let's define q1 for this. Q1 in this case gives me this particular square and this particular square. So it is the first square and the fourth square. Okay, and then when I run this particular process once again, these things are again subdivided, and even if I assume all of them survives, these smaller squares are indeed the subsets of this first big square, right?
Yeah.
Yes. So what does that mean? So this is the particular step Q2. Q2 gives you entirety of the first square. Okay, not even entirety of. Okay. So let's say in the fourth square, 3 of them dies. So what does Q2 gives you? Q2 gives you the entirety of the first square and only the third square from the square fourth of the previous thing. So this is the subset.
Yeah, sigma k you will get the 4 squares
You
from
have
the
the sets of those fours.
Yes.
You will not have the union of them. So rotationally, you have to define them as a union so you can go to the subset.
you can have the IDs of all 4 of the first square and then the third ID of the second square. Because it comes from sigma k.
Except
Yes.
first, second, fifth, sixth, and then it's 15.
So when I define sigma sub k plus 1, sigma sub k plus 1 gives me idea of all these 60 many squares. Yes.
It's not a union of points, right? It's just the squares separately.
Yeah, but those descending squares are eventually the subset of the bigger squares we had in hand, right? Okay, so if you have to be, I mean, overly rigorous with the notation, then okay, then I think this has, I mean, we could have written this in a better way. Okay, but
So like number of this.
okay, so what do you guys suggest for that?
Just take a union of I.
Okay, so like union of all those available i's.
Yes.
Okay, I mean, so union of all those surviving squares you try to say. Okay, I mean. Okay. So where was I? Okay, so yeah. So I defined that. Yeah, so this also got this finite that the fractal percolation basically is a direct Watson branching tree with Bernoulli P as the offspring distribution. Okay. So now if I try to find the probability that the entire tree eventually dies out, or if I try to find the probability that my q sub infinity eventually becomes phi, then what would that be? That would be, the fixed point solution of some q is equal to h of q, where h is the probability generating function of this binomial random variable. So basically, the probability that q infinity will eventually become phi is given by q is equal to p times q plus 1 minus p whole to the power in power. Okay. And if we try to find the probability that this thing happens almost surely, then what do we know? Expectation of this thing should be less than equal to 1. So what is the total expected number of offspring in a particular step? Total expected number of offspring in a particular step is given by p raised to the power n, because you have a total n power d number of squares, and in expectation p of them survive. So it is basically like expectation of a particular random variable. So p power n should be less than equal to 1. So p should be less than equal to n power minus d. So if that happens, if p is less than equal to n power minus d, then you can say that I don't really even have to talk about left to right crossing or anything, because after a finite number of steps, the resulting square will be just a blank bracket. But if p is greater than equal to n power d, then what happens is, the entire process can get wiped out with this particular probability q. So q is basically the lowest possible solution of this equation. So this is the basic model of random fractal percolation, and then you can extend the idea to various other prospects as well, and we will discuss about them in the very end of the talk. And now what we can discuss about is the connectivity properties of the resulting set. Because what can happen is, like say after a finite number of steps, let's say I am performing some subdivision here and there as well, all of these squares gets cancelled. So there is nothing in this every possible space. So this small square is not even connected to, okay, let's say this square survives. This small square is never connected to this particular square. So it is not even path connected, it is not even connected in a topological sense. So if we want to define, if we want to study the notion of connectedness, so basically what we will try to do, we will try to define two phases of fractal percolation. So at first, we will define a set Ex, and Ex basically set of all those points. Okay, so let us assume that we are restricting our discussion only in 2 dimensions and n is equal to 2 for now. So X is basically all those points in R2 such that, okay, not X, I should write Y here, such that X is connected to Y. Okay, so this is basically the set E sub X. Now I define 2 different phases. One of them is dust phase, so that is represented by E power t, and dust phase represents all those points in my resulting limiting set. Okay, so that is given to be Q infinite. So all those X in Q infinite such that all those points that is connected with X is the singular X. So these are the dust phase of the percolation. And if you want to define the connected phase, so connected phase is basically like to infinity minus the touch phase. Okay. So obviously from the previous discussion that we had, that if P is less than or equal to M by D, then this connected phase basically becomes phi, because the entire phase is dust. Oh, no. So sorry. In that case, this T infinity is itself phi, so we don't really have to talk about all of these things. But now what we can do, we will try to give a bound on the value of P such that for a particular range of values of P, this EC eventually becomes phi. So there are only some dusts lying around and here and there. So it is like this is your 0,1 square. So only some squares are survived here and there. They are not really connected in any possible way. So this thing happens when P is less than or equal to 1 by n. And there is a very good proof for that. So if our resulting set A infinite is connected, then at every possible n-level configuration, there exists a chain of squares which survives. So let's say I want to see the connectivity of these two particular surviving squares. Or okay, so rather than defining them in corner, for the simplicity we are defining them in sides. Okay. So if we want them to be connected, there should be a sequence of surviving squares like this in between them in every possible n-level configuration. So we say that there exists a non-trivial connected component. I mean, this particular event is a subset of intersection n greater than or equal to 1. There exists a horizontal crossing at level n. So at every if in any possible subsequent levels, if any of these squares dies out, these two basically become some two disjoint components. So if they have to survive in every possible level in configuration, all of these squares joining them should survive, and basically again they form a decreasing sequence, so we take their intersection. And like now, for the sake of heuristic or for the sake of proof rather, let us assume that rather than the stochastic, this model was kind of deterministic. So if the model was deterministic, how would you give the number of squares available in a particular level? So let's say you were having the fractal just like this. So this is the first square. Then each of these survives. Then each of these particular squares again survives, and that's how the fractal goes. So in a particular level small n, the total number of squares you have is given by n to the power n. So like if you perform only n is equal to 2 subdivisions, then at level 3 you will have 8 squares like that. So that's how the model grows. And as we have underlying Bernoulli random variable p, so we can sort of say that if we have to find expected number of squares that have survived in a particular n-level configuration, that is given by the theta of n power n times p. So it is basically like some constant value correction or some independent value correction which you can bound above or below by a constant. But to some extent it behaves like n power n times p. And then what we can apply? Okay, so there exists an n-level crossing. There exists a horizontal crossing in every possible level n. Let us call this particular event E hat sub n. So if we want to compute the probability of E hat sub n, we can give an upper bound by Markov inequality, that this is less than or equal to the expectation of this, and the expected number of surviving squares is given by this particular P times n equal to the power times some constant C, where this value of C is greater than 0. So that's how basically you can give an upper bound for the value of P of e power n. And after that, we will use the Bohr-Cantor lemma. So if we take summation of P of e power n hat, and you can see that this summation mentioned here is bounded above by this particular summation, and so as this is dominated above, and if P is less than or equal to 1 by n, this summation over here converges to 0. So this summation here would also be finite if this particular condition holds. So if we have P is less than or equal to 1 by n, we can say that probability of this particular things happens infinitely often eventually goes down to 0. So by Bohr-Cantor lemma, if P is less than or equal to 1 by n, then almost surely you will not have any connected phase in your resulting factor. So for those present here who don't know Bohr-Cantor lemma, so there are some small talks going on by the first year, so there our course will eventually discuss something about measure theory and probability as well. So if you guys are a bit unfamiliar about this Bohr-Cantor lemma, you might follow things from there. And yeah, so this is another interesting result that we can have. And after that, there are some more interesting things that can be covered. But okay, so if P is less than or equal to 1 by n, we have said that this thing would be this thing would be phi almost surely, and the entire thing would be dust phase. Okay, so whether we have a dust phase or a connected phase in our fractal, we can always talk about the fractal dimension, like the boxed out dimension or the house of dimension of the resulting set. Because in topological dimension, you can see that it is clearly going to be 1. Why it is 1? Because we are starting with a two-dimensional shape itself, but the most of the things are getting kind of like bracketed out. So if you do the calculation a bit rigorously, it eventually the topological dimension boils down to being 1. But if you want to talk about the fractal dimension or the house of dimension, then calculations become quite interesting, and for that I would refer to Ortina's talk on iterated function system and fractal dimensions. There she introduced a very good idea about how to compute house of dimensions and everything. So basically I have borrowed some machinery from there, and so again, like by now we all are kind of familiar with our fractal percolation model, so I won't be writing all the necessary symbols once again. So what we know is we have Q infinite that I will define now to be Q, that is intersection of all nth level configurations available. And now what I can do is, so now I will calculate the summation of diameter of a particular set Q to the power S. Okay, so for those people who are kind of familiar with house of dimension or like the house of measure, those will understand that if for a particular value of S, this eventually becomes 0 from infinite. So in house of measure, what we have is, this is the value of house of measure S, and this is the scale S. So it is infinite for some time, then for a certain value it eventually drops down to 0, and this particular value of disjoint transition, that will turn to be our house of dimension S. So in order to calculate the house of dimension, at first we compute this particular value. So what is the average diameter of a square cube in my percolation? So again it behaves something like big theta of P in power Pn, Now if you consider S is greater than log p in power t divided by log n, you will see that this particular summation over here eventually becomes 0. And if you consider S to be less than this particular thing, you will see that the total sum eventually diverges to infinite. So the fractal dimension, if you want to talk about the fractal dimension of this entire thing, I mean dimension fractal or dimension Hausdorff, that turns out to be b plus log p by log n. So it is actually a bit interesting to look at, because see, if you are performing your fractal percolation in three-dimensional cube, the Hausdorff dimension is actually a bit more than that actual dimension of the underlying ambient space. So this is a kind of fallacy that we can derive a bit rigorously, but still there is no physical justification that can be given by statistical physics or any possible mechanism we have in hand that why this thing happens. And after that, we can talk about some a bit generalized models, like some more generalization of this particular fractal percolation, and some problems which intuitively kind of seem obvious, but turns out to be not that obvious at all. So, one of the things that I would say is we can take any deterministic fractal, I mean we can generate any deterministic fractal using the definition of random fractal. How is that possible? For that we would at first define random substitution. So what is a random substitution? So let's say we are starting our fractal from the Q0 generation. Q0 generation is my entire d-dimensional cube, and from that I eventually go to Q1. Okay. Now in Q1 there are many possible configurations available, because any number of subcubes can die, all of them can survive, all of them can die out, anything can happen. So all of these possible configurations are given by omega 1, and that is basically 0, 1 to the power n power. Okay. And let's say E1 is a possible configuration which belongs to this big set omega 1. So if I am talking about my usual basic model, so this is one of the possible configurations available in omega 1. This is also one of the possible configurations available in omega 1, and so on. And the probability distribution or probability law defined on this set omega 1, I call it to be P. Okay. So by this P1, okay, so basically this set, this configuration A1 is chosen from my set Q0 with this particular probability, and after we get A2 via this process, so it is basically like an operation that we apply on Q1, and from that what we obtain is Q2. So basically like a particular configuration A1 is chosen, and again we apply some scaled down version of the P1 to that set, and then we get Q2, and that's how, and after that again some P2 of A2 is applied here, and this chain continues like this. So what happens in our usual fractal percolation, this P1, P2, P3, all of these pKs are same. They are basically Bernoulli random variables. Or if you want to take their sum, they are Bernoulli random variables. And A1, A2 are some possible configurations for which right now we don't really care. And now if I want to define a deterministic fractal from this, let's say Sierpinski carpet. So how does the Sierpinski carpet look? Sierpinski's carpet looks like this. So I have this. From this, only the middle square dies out. And again, I subdivide each of these into this tic-tac-toe shaped parts. And each of them, again, the middle square dies out, and the process continues. So if I want to generate this deterministic Sierpinski carpet using random fractals. So I will say that P of P1 of A1, this is a degenerate random variable. So it is 1 if and only if my A1 looks like this. And it is 0 otherwise. So that's how in every possible subsequent step you are getting only this possible kind of configuration and every other configuration is rejected and you are getting Sierpinski's carpet. Now you can also define random Sierpinski's carpet if you just replace this equal to by a subset. And what do I mean by a subset? A subset says that the middle square surely dies out, but each of the remaining square can be chosen, chosen to remain alive or chosen to remain die with a uniform probability. So that will also give you a kind of a Sierpinski's carpet, but there is a randomization involved. And there is a very interesting result about this random Sierpinski's carpet. This was first introduced by Deacon and Meester. So this was first introduced by Deacon and Meester in somewhere around 1980s. And they said that okay, it is intuitively very clear that if I fix n is equal to 2, then the critical probability of left to right connection and everything will be much higher than if I subdivide it into 3 parts, because as we increase the value of n, the randomization increases. So this has been kind of taken like a folklore. So the folklore means they have all confirmed it using simulations and everything, but till this present date, there is no proper rigorous proof available that if I take the critical probabilities as a function of n, that will be a decreasing function of n. So there is no such proof available. Or we can also define microcanonical fractal percolation that says that in every possible configuration, I just fix number of available squares. Okay, so in every possible generation, only m square will survive. So only their relative position is determined by randomization. So that is a very solvable model, and in that case, if we try to define the fractal dimension, so in that case, this big H of Q M is for microcanonical. That basically becomes log m by log n. So this m is basically in this case here replaced by p to the power nd, because p to the power nd in this case was expected number of boxes in every step, and here as we are fixing number of boxes to be n, so this thing is basically gets replaced by log n. Okay, so this also looks fairly obvious if we do some kind of calculation, but it is still unknown that whether the box dimension of this is equal to this or the box dimension is greater or less. There is no proof available. There is no proof available for microcanonical percolation, so again there is no proof available for the general percolation model as well, because there this number m also varies very rapidly. And after that, while studying porous rocks, statistical physicists came up with a very interesting model, and that is known as Swiss cheese model. So Swiss cheese, I guess all of you guys have seen it, the famous cartoon Tom and Jerry, that there is a block of cheese like this, there is some part obliterated from here, some part obliterated from here. So they basically saw fractal percolation model and tried to implement this Swiss cheese model to study the porosity or connectivity through a very porous kind of rock, or even in bedrock, while trying to study water channels. So in that particular model, what they did was, they took a cube and, okay, so we can talk about our three-dimensional unit cube, but again, you can rescale everything, reposition everything, apply rotation and everything basically becomes invariant. So I will just talk about my usual three-dimensional cube. Like this. And here what happens, from this cube, okay, let's say for now this cube is 0,1 cube, and what they do, they uniformly pick up some points from this cube. They can be inside the cube, over the surface, in the edge, everything possible. And okay, so not always they pick this up uniformly. There can be an underlying Poisson random variable as well. In that case, we call it a Poisson point process, and all of this can be done. And after that, from a set of available radius, they pick up a certain number of radius. And what they do, okay, so let's take this cube to be capital C. And what they do is they define D of, okay, let us randomly chosen point be PR, and the radius is R. And they take their intersection with C. And after that, they remove the intersection from the cube. So it basically looks like some piece is missing from here, some particular piece is missing from here. And then they try to arrive at a limiting model by either varying this value of R as a sequence of real numbers, or by varying the value of PR to choose these points. So eventually the model becomes very, very porous, and they try to study the arc percolation over this model. And what they do is, so arc percolation is basically study path connectivity. You took two random points, whether they are connected by a path or not. So if this point is A and this is B, you define a path to be gamma of A is equal to 1, gamma of A is equal to 0, gamma of B to be 1, and gamma is not equal to gamma B, and for any two intermediate points, the values are not same, gamma is a continuous function and everything. I mean, just the general way we define path connectivity in homology. So, this is a very well studied model, well understood as well, easy to visualize. But still we don't have any answer about any critical probability, I mean any possible critical probability. So whether there will be a left to right crossing, is there any bound or any possible value of left to right crossing? So even if we have an infinite stack of this, so if we extend this infinitely in every possible direction, will there always be an infinite cluster? Does the path always behave like a self-avoiding path, or it is a random path? We don't have any possible answer on this model as of now. So apparently all of these models derived from random fractals are to some extent pretty easy to understand, like the very basic understandings and everything, but there remains a lot of open questions. So am I missing anything interesting? No. Yeah. Okay, so there are some extra information available. So like while preparing this talk, I use a couple of references. You can go to the references and check out more if you want. So some of the references are like one is aspects of percolation. This is by Lincoln Charles. One is some handouts on Aritrabha theory. So it is basically intro to Bernoulli percolation. This is by Hugo Dominguez Open. And this particular last material gives you a very fair and square idea about the topology of these spaces and all the other related models. That is by that is basically recent progress in fractal percolation. That is by Todd Sheet and Kosovo. Okay, I will just give you an idea about how recent this recent progress is. So the last research that has been done on this particular topic was by Deakin, Meester, and all of these guys, and that was somewhere around 1980s and 1985. After that, we have done much work about some related fields like Swiss-Cheese model, and from that Curie-Weiss model and some other models of statistical physics. But this particular topic, fractal percolation, its critical probability, these open questions regarding these are still untouched in this day. So, although these models are fair to understand, or it is easy to see that there will exist some left to right path, top to bottom path, and everything. But some results might be confirmed by simulation, but there is no any proper proof available. So, I think it's a good place to stop. Any questions?
No questions? Thank you for this great talk.